In this video, we're going to have a look at rectilinear motion and how we find the displacement function from the velocity function. From our previous work, understanding rectilinear motion, which is the motion of a particle in a straight line, we've been using x to represent our displacement with respect to time. We know that displacement is positive, it's moved to the right of the origin. If it's negative, it's moved to the left. We also know that to find the velocity, we need to differentiate the displacement function. And so today we're going to look at if we know the velocity function, to find the displacement, we need to anti-differentiate the velocity function. Now we know that comes with a constant of integration, the plus c, but we know if we've got sufficient information, we can find that constant. So the diagram I've shown here is just to remind you about how we deal with these displacement and velocity and in fact acceleration functions of a particle moving in rectilinear motion. So we're going to have a look in particular about how we're going to go from velocity back to its displacement. In our first example, we've got a particle travelling in a straight line such that its velocity is given by v equals 6t squared plus 4. After 1 second, the particle is 5 meters from the origin. We want to find the displacement of the particle after 2 seconds. So what we know is the velocity is 6t squared plus 4. So we can easily find a function for the displacement by doing the antiderivative. So we're going to add 1 to the power of t and divide by the new power and add in that power of t to the 1 and a plus c. Now we're going to use that information that we have that when t is 1 second, x is positive 5. So we're going to use this to solve for our constant of integration. So we're subbing in, we can simplify our function here. So we've got 5 equals 2 plus 4, which would be 5 equals 6 plus c. So our c is negative 1. So we have our displacement function with respect to time of 2t cubed plus 4t take 1. So now we can actually answer the question, what is the displacement after 2 seconds? So subbing 2 into our function, we end up with 23 meters. In our second example, we have a particle that travels along a straight line with its velocity given by v meters per second at 4t plus 1. Find the distance travelled in the 5th second. So we're asked for something a little bit different in this question. We're asked for distance. So we're not worried about whether it's to the left or right of the origin. We just want to know how far it has travelled and in the 5th second rather than after 5 seconds. So if we start with our velocity function of 4t plus 1, the displacement is going to be x equals 4t squared over 2 plus t plus c. We can simplify that to 2t squared plus t plus c. Now, unfortunately, they don't give us any other information to find our constant of integration. However, in looking at this question, it's asking us to find how far it's travelled in the 5th second, which means after the 4th second to the end of that 5th second. So in fact, what we're being asked to find here is the displacement after 5 seconds and taking away the displacement at 4 seconds and finding that distance it's travelled. So in fact, we can substitute straight into this and we'll find that our c, our constant of integration, will disappear. So putting in when t is 5, we've got 2 lots of 5 squared, which is 25, plus a 5 plus a c. And then we can take away 2 lots of 4 squared, which is 16, adding in that 4 and adding in c. And we realise that our c values now, when we've got 55 plus c, take 36 and take c, will end up cancelling. We end up with a value of 19. So we can say that the particle travelled 19 metres in the 5th second. So in our third question, we've got an object moving along a straight line with velocity represented by a quadratic function in metres per second. And when the displacement is 6 metres at t equals 3 seconds. What I'd like you to do is pause the video and find part A and B. Find its velocity at 2 seconds and its displacement at 6 seconds. And come back and unpause the video and we'll go through our solutions. Okay, so the velocity at 2 seconds is going to be substituted in here. 2 squared is 4, take 2 lots of 2 is taking 4, take 8. We find we have a velocity of -8 metres per second. The displacement when t equals 6 seconds, well, we need a displacement function. So we're going to anti-differentiate. So we're going to end up with t cubed over 3, subtract t squared because the -2 cancels with the divide 2, and take 8t and plus c. We're going to use that fact that at t is 3 seconds, the displacement is +6, substituting that in to our displacement function, popping in that 3, we end up with 6 equals 9, take 9, take 24 plus c, so c is in fact 30. So we've got a displacement function of t cubed over 3, take t squared, take 8t plus 30. Therefore, our displacement at 6 seconds is going to be 18 metres. So let's consider part C. The distance travelled by the object between the 3rd and the 6th seconds. So this time we want distance, so we're not worried about whether it's to the left or right. We just want to add up the total distances between 3 and 6 seconds. So one of the key things to do here is get a bit of an idea about the information about its movement so far. At the moment, we know its displacement at 3 seconds is 6 metres. We've just worked out its displacement at 6 seconds is 18 metres. We obviously know, because we've got a quadratic representing the velocity and a cubic representing the displacement, we could have up to 2 times where it stops and changes direction. So we need to find out when the velocity is 0, find out when it is momentarily at rest. So if we grab our velocity function and find out when it equals 0, we can factor this and realise it happens when t is -2 and when t is 4. But as time is obviously greater than 0, we only have one time that we're going to consider when the particle is at rest. So we want to find out the displacement when t is 4, and we find that at 3 1/3 metres. So now let's get a bit of a picture of what this looks like. So let's draw a bit of a scale in, putting 0 in as our origin. And we know from our displacement function, if we have a look, when t is 0, we end up with +30. So we know that the particle starts 30 metres to the right of the origin. It moves to the left because at 3 seconds, it's down to 6 metres. So we'll put t equals 3. We know at 4 seconds, it's at 3 1/3 metres, and it turns around. Changes its direction. We know at 6 seconds, it's at 18 metres as well. So between the 3rd second and the 6th second, we need to find the total distance that I've highlighted. So the total distance is going to be represented by these two pieces between 6 and, or a piece between 6 and 3 1/3. So 6 take 3 1/3, and then the second piece is from 3 1/3 up to 18, so the difference there. And we work this out, we find out our total is 17 1/3 metres that is travelled between the 3rd and the 6th second. So this is just an example of being able to use our ability to anti-differentiate to move from velocity back to displacement. And remember, the diagrams of rectilinear motion are really key in looking at when a particle stops and turns around, and also its displacement from the origin initially and as it moves.